Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is Atiqah binti MAMAT from AS2536A1. My metric number is 2021899642. As for today, I will be presenting on my final year project supervised by Professor Madia Dr. Muhammad Tajuddin bin Muhammad Ali with the title of Synthesis of Betulinic Acid-2 for dihydroxybenzylidine hydrazone. So here is the agenda for today's presentation, starting off with background of study, followed by problem statement, significance of study, objective, literature review, methodology, result and discussion, conclusion, and lastly will be some recommendation for future study. Betulinic acid is one of the example of natural product that has been shown to exhibit various biological and pharmacological activities. Betulinic acid is a bioactive pentacyclic lupine type 3 terpene. In 2023, Mu et al. Reported in his research that betulinic acid, also referred as BA, can be gained through plant extraction but yield a very limited amount of BA since it is known to exist in a very low concentration in plant sources. Therefore, many synthesis methods has been introduced, including chemical synthesis, metabolic engineering, and biotransformation to increase the production of betulinic acid. Betulinic acid has a significant potential against a wide range of tumor cells, which is the reason why it is widely used in pharmaceutical industry. In fact, in the previous studies has shown a wonderful effect of betulinic acid in inhibiting HIV, inflammation, and function as analgesic and antiemetic. Despite having an excellent anti-cancer activity, betulinic acid has poor solubility and low bioavailability. Poor solubility means that it is harder to be absorbed, while low bioavailability means that a larger dose is required to reach a minimum effective concentration of a particular drug. Thus, derivatization of betulinic acid was to produce a better compound with more powerful therapeutic effect. Hence, this study is to synthesize betulinic acid hydrazone as one of the derivatives that might have higher bioactivity suitable for pharmaceutical and medical purposes. There are two objectives to be obtained from this research. The first one is to synthesize betulinic acid-2 for dihydroxybenzylidine hydrazone. Secondly is to analyze the compound through spectroscopic analysis such as NMR, IR, and GCMS. Let's first go through the literature review that I had done. As you can see, here is the structure for betulinic acid with chemical formula of C30H48 and O3. According to the study by Mu et al. In 2023, betulinic acid is primarily extracted from the bark of plants from Betulinaceae family or can be chemically synthesized. So here is one of the ways to chemically produce betulinic acid, which involves two steps of reaction. It started off with oxidation of betulinol to betulonic acid by using Jones reagent, which are chromium oxide, sulfuric acid, and acetone. Further reaction is reduction of betulonic acid by sodium borohydride into propanol to obtain betulinic acid. It is reported that the yield can reach over 90% by using this method. Now, let's take a look at betulinic acid derivatives. Here is one of the examples for synthetic routes of betulinic acid derivatives in multi-step procedure. As synthesized by Y. Zhang et al., betulinic acid, which referred to as compound number 1, was converted to benzyl ester, compound number 8. In DMF and potassium carbonate under the temperature of 85 degrees Celsius for the protection of carboxylic acid. The activated ester, compound number 9, was obtained by reacting compound number 8 with nitrophenyl chloroformate in the presence of base DMAP at room temperature. Coupling of compound number 9 with pyrrolidine and triethylamine in DCM at room temperature resulted in the synthesis of compound 10A to 10B. The final target compound 11A and 11B were afforded by the deprotection of benzyl in a palladium catalyzed hydrogenation. For the experimental part, let's begin with methodology. In order to synthesize betulinic acid-2 for dihydroxybenzylidine hydrazone, there are three steps to be worked with. Firstly, esterification of betulinic acid by using diazomethane. Betulinic acid was mixed with methanol and a freshly prepared diazomethane is added to the mixture. The mixture was refluxed and left to stir overnight under the nitrogen conditions. On the next day, the mixture was diluted with dichloromethane and 10% aqueous acetic acid was added to remove the excess diazomethane. Betulinic acid ester was then extracted from the mixture by using a separating funnel. Secondly, reduction using hydrazine. The obtained BA ester was added with methanol and hydrazine monohydrate. The mixture was refluxed for 6 hours when the temperature reached about 70 degrees Celsius. The reflux sample was then dried with a rotary evaporator, and then it was diluted with dichloromethane, and it was extracted again using separating funnel to afford pure product of betulinic acid hydrazine. The last step was to synthesis betulinic acid hydrazone compound by further reduction of betulinic acid hydrazine with substitute 2,4-dihydroxybenzaldehyde. Previously produced betulinic hydrazine and 2,4-dihydroxybenzaldehyde were mixed with glacial acetic acid. The mixture was then dissolved in methanol and refluxed for 6 hours. Upon completion, the sample were dried using rotary evaporator, and the product was collected and rinsed with diethyl ether to afford the final product of betulinic acid 2,4-dihydroxybenzaldehyde hydrazone. Betulinic acid ester, betulinic acid hydrazine, and the final product were run for NMR, IR, and GCMS. However, in this video, I'm going to mainly focus on NMR result. The analysis of the obtained data focus more on the active site, which are at C3, C20, C28, and C29. Based on the spectrum, proton NMR shift of betulinic acid ester in CDCl3 indicated the presence of 6 methyl groups bearing proton at C30, C27, C26, C25, C24, and C23, which were observed to resonate at signals within the range of 0.6 to 1.6 ppm. As you can see from the table, both protons for H29 resonated as singlets at 4.69 and 4.52 ppm. Proton of the ester group seems to appear at a chemical shift of 3.5 to 3.59 ppm. Meanwhile, one proton of hydroxyl group and one proton at H19 were resonated at signal of 3.15 to 3.24 ppm and 2.3 to 2.95 ppm respectively as multiplets. Next is carbon NMR of BA ester. The hydroxyl group attached to carbon 3 was portrayed to be shifted at 79.03 ppm, and carbonyl group at the position of carbon 28 showed a signal resonance of 176.78 ppm. Both C for the olefinic group at carbon 20 and carbon 29 were resonated at signal 150.61 ppm and 109.7 ppm respectively. Chemical shift of 51.73 ppm indicated the presence of ester group or CH3 at C31. Now let's move on to the second compound, which is BA hydrazine. Same goes for this compound. The presence of 6 methyl group were observed to resonate at signal range of 0.6 to 1.6 ppm. Different from BA ester, BA hydrazine showed an additional peak at 5.22 and 5.11 ppm to represent the presence of hydrogen attached to the nitrogen atom of hydrazine group. In fact, there was no peak observed for ester in BA hydrazine as compared to BA ester. For carbon NMR of BA hydrazine, there was no peak observed at C31 like in BA ester. However, the other unique functional groups could still be observed. For instance, carbon 3 bearing the hydroxyl group was resonated at a chemical shift of 79.59 ppm. The most downfield signals at 176.8 ppm represented the peak for carbonyl group that was located at C28. The olefinic group at C20 and C29 were observed to appear at chemical shift of 150.68 and 111.03 ppm respectively. Then, let's proceed with the last compound, which is betulinic acid 2,4-dihydroxybenzaldehyde hydrazone. Proton attached to the nitrogen atom could be seen to appear at 7.56 to 7.62 ppm as singlets, and the other proton are the same as in BA ester and BA hydrazine. Proton of hydroxyl group at C3 was observed as multiplet at 3.19 to 3.24 ppm. Another multiplet signal was observed indicated the presence of proton at H19 with 2.9 to 2.94 ppm, and again two singlet signal represented two protons attached to C at 4.6 to 4.65 ppm and 4.62 to 4.7 ppm. The same goes for carbon NMR for this final compound. The peak for carbonyl groups at carbon 28, hydroxyl group at carbon 3, and C double bond C at C20 and C29 were observed. In fact, there was additional peak at carbon 31, depicting the presence of C double bond N at chemical shift of 137.9 ppm. The existence of aromatic ring of substitute 2,4-dihydroxybenzaldehyde was indicated based on C double bond C at carbon 32 with 136.1 ppm, carbon 34 with 115.3 ppm, carbon 36 with 121.9 ppm, and carbon 37 with 103.19 ppm. The two hydroxyl groups attached to the aromatic ring of the substitute aldehyde could be seen at carbon 33 and carbon 35 that were resonated at signals of 164.2 ppm and 164.33 ppm respectively. To conclude, this study has explored the synthetic pathway and suitable method for synthesizing the final product, which was hydrazone derivative of betulinic acid. This derivative may exhibit an improved solubility, stability, and biological activity, making it a valuable candidate for drug development. Thus, further research should focus on refining synthetic strategies, enhancing compound selectivity, and exploring new therapeutic applications of the betulinic acid for pharmaceutical purposes. Moreover, to optimize the biological selectivity and activity, it is recommended to explore multiple chemical modification and derivatization methods to produce a more powerful and effective compound. I think that's all from me. I'm going to end my presentation here. Thank you.